All right, our aircraft in the 90s problem is one that was about linear regressions. And so here we have a residual plot and we have a computer printout. And so we're talking about that relationship between the X and Y data. So, first, talking about if a linear model is appropriate, you cannot just look at the correlation coefficient. You have to see if there is a pattern in the residual plot. So, that's what we were looking for. And in here, in this case, there was not one. So, yes, there is no pattern in the residual plot, is the reason that we know that linear model appears to be an appropriate model for the use of this data. Now, then it says, what's the value of the slope? And interpret the slope. Interpret the slope. So here we have this. We can see that years is our x variable and 233.517 is the slope. So for every one increase in the years, the x, which is the year since 1990. So for every additional year after 1990, the predicted y, that's the predicted number of commercial aircraft flying, increases by 233.517 aircraft. Okay, context. And what's the value of that y-intercept? Interpret the y-intercept. So here we have 2,939.93. It happens when the x is 0. So that means in 1990, because that's when the x was 0. So in the year 1990, the predicted Y is this. So there's predicted to be 2,939.93 commercial aircraft flying. Okay. And then, of course, here is our using that prediction equation, predicting the number of aircraft in 1992, which means that X value is 2. So I plugged that in. And there we have that aircraft value, the predicted aircraft value. Remember, we're keeping straight predicted versus what actually occurred. Okay. So now, what was the actual number of commercial? Well, let's take a look up above, because up above, then I can see here in 1992, okay, the residual was 40. So that means the actual was 40 above what was predicted to happen. So therefore, you could do that a couple ways. You could just say, predicted was the 3406, and I want to go 40 above that. So common sense says we're just going to add that to it. And if you're a formula driven person, then here you can say, residual RAP, residual R equals A, actual Y minus P. RAP, residual equals actual Y minus predicted Y. And then you can just plug in what you know and what you need to know and solve for what you need to know. So here we go. Now, interpret S. S on that previous page is the standard deviation right here, standard deviation of the residuals. And so that's saying on average how far these actual are away from what they were predicted to be, the actual y, how far the actual y was from what it was predicted to be. So the average amount that the actual number of commercial aircraft varies from predicted number of aircraft was 33.43. The average amount that the actual y value point varies from what's predicted to become, varies from the predicted y. All right, and so then now here it says create and interpret a 95% confidence interval. So that process of creating an interval is a panic model. So technically, you were supposed to do a panic model right there. And so I did without doing the assumptions. Okay. Honestly, in the answer key that I got from another teacher who had written these extension problems, didn't do a complete interval. And later on down, really, you were supposed to do a complete test when later it asks if there's statistical evidence of something. So just keep that in mind that whenever it asks for an interval, you should do a panic. And when it asks for statistical evidence, you should do a phantoms. You should run a statistical test. So Here we go. So I defined the parameter. Beta was that slope of the relationship between year after 1990 and the number of commercial aircraft. It was a linear regression T interval. So we had to do it by hand from a computer printout. Remember, that's that sample slope plus or minus the critical T score times that standard deviation of the slope. So here we have that 233.517 plus or minus this this T critical value T star I got from doing inverse T of one tail, because remember, if you put 95% in the middle, then that puts 0.025 in a tail. So we've got 0.025 in the tail. And now 6 degrees of freedom. Hmm, where did I get that from? Well, um, I counted the number of pieces of data on the front, and there were 8 pieces of data on the front. And since there's 8 pieces of data on the front, and for linear regression, 2 variable data, then you have sample size minus 2. Then here we have 6 degrees of freedom. Okay. So I am 90. Oh, so there's my interval. And so I am 95% confident that the true slope of the relationship between year after 1990 and number of commercial aircraft is flying is between 222.94 and 244 planes per year. So that's about how much it's increasing each year. And then looky here, R squared. That's that coefficient of determination, the percent of variation that is found in the Y. So about 87.4% of the variation in the Y, which is the number of aircraft flying, it can be explained by the changes in the X, or it can be explained by the model itself, that linear relationship between uh, or like linear relationship with year. That's an easier way to say that. Okay, but it's that percent of variation in the Y that can be explained by that linear relationship with X. So find and interpret the correlation coefficient represented by the R. So I did the square root of that R squared. Make sure you look at the slope to determine the sign. The slope was positive, so therefore I know R is positive. So there is a strong, there is a weak, positive or negative, linear. So that is your you're describing the relationship there. So that's another key phrase to look for. If they want you to describe the relationship, do the direction, if there's any unusual features, the form, that's linear versus nonlinear, and then the strength. So here we have a strong, positive, linear relationship between year and number of aircraft flying. So now we're going to transform the number of additional airplanes per year with that $1,000 regulatory cost. So each year on average, then that's how much it is increasing, because you can just multiply times the slope times the 100. There was no additional component there to add. And then here is there statistical evidence that the number of aircraft is related? There is a linear relationship uh, with year. So do we have statistical evidence only with a p-value? So here we go. Beta is that slope of the relationship. The null hypothesis being no linear relationship, and of course, alternatively, yes. So we did a linear regression t-test. So I went and ran that on my calculator, the t-score. Oh, no, I didn't go run it on my calculator because I didn't have that information to do that. I got that from this computer printout. Easy peasy, right here. There was your t-score and your p-value. So you've got those right there. And then don't forget to list the DF, must include the DF. So there you go. I got those information from the computer printout. So our p-value of 0 is less than alpha of 0.05. So we're going to reject the null hypothesis. And since p-value is less than alpha, there is evidence that there is a linear relationship between the year and the number of commercial aircraft flying. All right, so there was our linear model, all of our bivariate data problem to work through and remember the things that are critical for that unit. So I hope that helped you to remember some of those key points.